Okay, so I'm gonna get started. So really appreciate the kind introduction. Thank you so much. And I'm really excited to be here to talk about some of my recent work on learning structured world models from and for physical interactions. And the overall goal of today's talk is that by the end of my talk, you'll be convinced that we should add structure to our learning systems. And with a suitable choice of structures in the systems, we'll have much better sample efficiency and generalization capabilities, especially for complicated physical interaction tasks in the real world. And today I'm going to showcase examples of manipulating, for example, dough, granular objects, as well as crafting dumplings. And it's all thanks to the structures we add to our dynamical systems that can predict the futures and help us to do plannings in the real world. So the North Star of my research is to build robotic manipulation systems that can achieve human-level manipulation capabilities. And although we have robotic manipulators currently deployed in the industry for commercial use, they typically handle relatively simple objects for pick and place tasks. Yet we humans can perform much more complicated manipulation tasks. For example, we can crack eggs, spread butter on a slice of bread, making dough and sushi. All of these capabilities goes far beyond of what's possible using the current robotic systems. So I would like to argue that one of the key enabling factors of why we humans can perform these tasks is these intuitive models of the world, that we can predict how the environment would change if we apply a specific action. For example, looking at the following two videos, although the manipulating objects are very different from each other, one is dough and the other is a pile of onions, we can effortlessly predict the effect of our actions. For example, how the dough will deform and how the onion pieces will move around. The predictive ability then help us plan our behavior in order to achieve a specific goal. And to build such a predictive models, there are generally two ways of doing it. One is to learn the model from data. We can roughly categorize it as model-based reinforcement learning. The typical framework typically maps the observation into a latent space Z, and then learn a dynamics model predicting the evolution of the latent space. You can learn directly from partial observations and handle systems where the underlying dynamics is uncertain or unknown. We have success stories, for example, like MoveZero and controlling robots from pixels. However, most prior work typically assume that Z is one-dimensional vector, which is unstructured and limited in terms of generalization. For example, when looking at the Play-Doh or a pile of coffee beans, we humans are not thinking of them as just one single latent vectors. We can recognize the constituting components and the relational structures between them. And it's exactly the structured understanding of the environment that allows us to handle objects and systems with complicated physical properties and complicated interactions. Talking about structure, the other way to build a predictive model is based on analytical physical equations like F equals ma. This is arguably the most compact ways to encode the structures and has excellent generalization. It is also extremely useful in constructing models, for example, for Boston Dynamics robots and rockets. However, such physics-based model relies on the assumption that full state information is available, which is often not the case for complicated physical interaction tasks. For example, in the onion piece manipulation tasks, estimating the states of each and every one of the onion pieces is very hard and sometimes impossible. Or for the short bottling task, although we humans can only manipulate and do this task based on local information, but you want to have a simulator and simulate this whole process. We need to know the full state of the clothes before we can use the physics-based model to model the interactions. So both methods have their pros and cons. The left is model learning, while the right is structures in the model. My research aims to bridge the gap and get the best of both worlds, then learn models from the robot's interactions with the environments. We want to add structure to the model, then capture the compositional structures of the underlying physical systems. And the agents learn from the interactions and use this learned model to do better physical interactions in the real world. To make the problem more concrete, we aim to minimize an objective function C, defined over the observation Y and the action U. And we have to think through three most critical constraints. The first one is a perception module that essentially maps the observations into some scene representation Z. Then is a dynamics module that predicts the changes in the scene representation when given an external action. Then is a control module that derive the control signal based on the scene representation to minimize the task objective. If you look closely at this problem formulation, you realize that the choice of scene representation Z has a profound impact on the design of all components throughout the entire system. Thus, it is of paramount importance to think carefully on what kind of representation we should use for a given task and understand its implications about the system structure. I will show how a suitable choice of representation and structure can lead to better generalizations and sample efficiency. And for this specific talk, I'm focused on the use of particle as a representations. Particle as a representation is a very general representation and is very flexible in terms of representing objects of wide variety of materials, like rigid objects, deformable objects, and fluids. As you can see from the images, different objects consist of particles, which indicates the object geometry and the interactions within and between the objects. And to model the dynamical system represented using particles, we are using graph neural networks. Here is a graphical illustration of how graph neural networks work. This graph contains 3 nodes and 3 directed edges, which together is our scene representation Z. For each directed edges in the graph, we denote the sender as B and the receiver as A. An edge encoder takes the information on both the sender and receiver and outputs an edge representation, which we denoted as EK. Then for each node, we aggregate all the edge representation on edges where node A is the receiver. Their aggregation is then combined with the information on node A to derive the node representations in the next time step. We can then define the loss function between the nodes or edge representation and the quantity we care to supervise the model. In our specific case, what we care is the evolution of the state. Hence, the loss function is a mean squared error between the node representation and the actual state at the next time step. One thing to note here is that we exploit the compositional nature of the system, where the node encoder is shared among all nodes and the edge encoder is shared among all edges. Thus, the NERD model can generalize naturally to systems of different sizes or even outside the training distribution, as we will show later in the experiments. Using the graph neural dynamics models, we'll be able to model systems, for example, here, 2 fluids fall down and merging with each other, where the left is a ground truth and the right is our model's open loop prediction. By open loop, I mean that the inputs to our systems are only the initial states of all particles, and want to predict how the particle is going to evolve for a very long future horizons. As you can see from the video, the prediction is very close to the ground truth. Here's another example where we grip a deformable materials using 2 cuboids, which are to mimic the 2 fingers of a parallel gripper. Here we show some other examples of shake a box of fluids. We're assuming here that the container is fully actuated. Our model accurately predicts the long horizon future by taking in the particle state at the first frame and the subsequent actions for control container's movements. As we have discussed before, all nodes share the same node encoder and all edges share the same edge encoder. So our system can naturally generate to systems with more particles than during training. This example shows that our model can work in an environment containing 2 times more particles than during training. It is clear from the video that our model captures the wave of the fluid particles, and it can also maintain the density and incompressiveness constraints of the fluids. After we have obtained a dynamics model, how can we use it for the control tasks? In this work, because the NERD model is a neural network, which is naturally differentiable, which we can extract the gradients using off-the-shelf packages like PyTorch and TensorFlow. We can then using gradient descent to optimize the action signals and apply a model predictive control framework to account for the modeling error. More specifically, here we use the blue dots to represent the initial state of the systems. The goal is to achieve the target shown in red. We have an initial guess of the action sequence and use the learned model to predict the control outcome. We then define a loss functions that describes the distance between the predicted outcome and the targets, and then backpropagate the gradients of the loss function with respect to the action sequence. We then iteratively update the action sequence to minimize the distance between the predicted outcome and the target. The model may not be accurate enough because it's a data-driven model. So we use model predictive control, where we only execute the first action U0. The environment will give us a new state Z1. We then re-optimize the action sequence, again, using gradient descent to give the model an opportunity to adjust its action sequence to account for the prediction error. And this is essentially a shooting method if you are familiar with control. And the key to the success of this method is to leverage the parallel computing power of GPUs. We can sample hundreds or even thousands of action sequences at the same time and do gradient descent for all of them simultaneously. This allows the planned trajectory to perform local refinements and at the same time get around some local optimum. And here we show some models control results. The goal here is to shake this box of fluids where the control signal is the position of this fully actuated container. We want the shape of the fluid to match the shape shown on the top left when the countdown goes to 0. And here's the control process. And here's the result. Here's another example. It's clear from the video that our model's dynamics prediction capability can help the container minimize the distance between the end states and the targets. Here we show the control results in manipulating a deformable form. The decision variable here is the position, orientation, and the clipping distance of the parallel gripper. And after 2 grips, the result roughly matches the targets. Here's another example. And after a few grips, it is much closer to the targets. We have also generalized the learned model to the real world by manipulating a deformable form in the real world using a real robot. Here we show 2 examples of manipulating these forms into a target shapes. The first row is a T-like shape, and the second row is a tilted shape. After a few grips, the shape is getting closer to the targets. And the key to the success of this method is to conduct real sim-to-real transfer, where the model is learned using a physics-based simulator. And in order to transfer to the real world, we use 3D reconstruction to obtain the shape data and online adaptations to estimate the physical parameters, such as stiffness. This raises the question of whether we can eliminate the reliance on the physics-based simulator, because we do not have a physics-based simulator that can simulate everything around us. And we are also asking whether we can directly learn the model from real data, because we do not have simulators. Everything needs to from the interactions and from the data where the robot is obtained through its interactions with the real environment. And we are also asking, can we move to some more complicated tasks? I'm from China. So given that I already work on the manipulations of elastoplastic objects, so I thought, why not try to make some dumplings? Let's see how well we can proceed using real data without relying on physics-based simulations to learn models that allow us to make a dumpling. Making dumpling is no easy task. We have to, once again, work with elastoplastic objects that possesses extremely high degrees of freedom. Simultaneously, we must account for excessively large deformations in the dumpling making process and handle instances involving the splitting and merging of materials. In addition, this is also a long horizon task that requires the use of a series of cutting, modeling, and clamping tools. It necessitates the agents to make both discrete decisions on which tool to use and the continuous decision on what specific action to take. To construct a robotic system capable of tasks as complicated as dumpling making, we first design a tool set, referencing tools commonly used in our daily life in our kitchen environments. We included 15 3D printed tools consisting of grippers of various shapes, as well as rollers, pressers, and cutters, and spatulas of different sizes. The tool set incorporates both non-actuated tools like presser, where the pressers will move together with the movements of your end effectors. It also contains actuated tools like grippers and spatulas, where we are using the fingers of the end effectors to control the openness and closeness of these different tools. We then design a tool switching system capable of efficiently transitioning between the tools. Here, as marked by the white ellipses, are 4 RGBD cameras we use to observe the environment to get a 3D reconstructions of the dough we are manipulating. And this red rectangle indicates the workspace we are working in. Here we have the dumpling making process. What's particularly interesting about this video is the presence of a human persistently perturbing the robots, hindering the progress. we demonstrate the robustness of our proposed framework during real-time executions in this video. Let's begin. After the robot cuts the dough, the humans puts the excess dough back. The robot knows it needs to cut again to get the right volume. Then the humans grips the dough into some irregular shapes. But the robot can still accurately achieve the next sub-targets with guidance from a self-supervised learned policy network. Yep, and the robot grip again, then the humans is constantly making perturbations. And then is the presser. After the robot presses the dough, the humans pinches the dough into, for example, a lumpy shape and add stuff to it. And the robot realizes you have to press multiple times to flatten it. Next is rolling. After the robot rolls 2 times, the robot folds the flattened dough into a thicker shape. The robot rolls again to ensure that robot surface area is large and flattened enough to cut a circle out of it. After the robot cuts out the circle dumpling shape, this is where things gets interesting. Here, the human shows no mercy and destroy everything the robot has just accomplished. And the robot puts down the roller and pick up the knife to start again from the beginning, demonstrating the robustness and I dare say the patience of our framework in the face of heavy disturbance. The robots then use a pusher to push away the excess dough. Next, we have the dumpling skin ready. Then the robots will use a spatula to move the skin into the dumpling clip. And then the robots will use a spatula again to put the fillings onto the dumpling skin and use a hook to move the handles to press, to close, press, and open it to finish the dumpling making pipeline. What enables this demo is the closed loop control system that takes the current observation on the left and the targets as inputs. And we have a classifier that is trained to predict what tool to use at this current stage, which is essentially making a discrete decision. And conditioned on the selected tool and the observation and the target of course, a policy network determines the specific action to take. And after the robot took the action, the environment will change, and then new observations is gonna feed back to our interaction systems to close this perception and action loop. We utilize a self-supervised learning approach to learn the policy. And at the core of this self-supervised learning procedure is a learned dynamics model, instantiated as a graph neural network operated on this particle-based representation that's used to represent the dough. And this graph dynamics model is exactly the same as what I described in the first project. The learned dynamics model functions as a simulator, or you could also think of it as a generator. This enables us to distill a policy for efficient feedback control during testing. And on the bottom right, you'll be able to see that we are using different types of parameterizations for different tools, but we are using the same representations using the particle to represent the geometry of the tools and the dough to model the system. More specifically, this graph neural dynamics model takes the current observation, again, similarly, as inputs and iteratively predicts the future states conditioned on the input action. And represent the current state using the point clouds of both the dough and the tool, which allows for a more accurate modeling of the geometry and their interactions. Here we present a comparison between the ground truth and the long horizon future prediction results obtained using our learned dynamics. The first row displays the prediction, while the second row presents the ground truth. As you can see from the image, our learned model accurately captures the geometric deformations of the dough, laying a solid foundation for the model to learn a policy on top of it. Here is another example of using pressers to deform to make the thickness of the dough thinner. And one very important point I want to emphasize here is that thanks to the structures we introduced using the particle representation and the graph neural network, remember, the node encoder is shared among all nodes and the edge encoder is shared among all edges, which essentially are sparse structures where the number of parameters we need to learn doesn't scale with the size of the systems. It only scales with the type of edges or type of nodes in your systems. So you can naturally generalize. So that's why with just 20 minutes of real-world interaction data for each tools, we can learn a reasonably accurate dynamics models. And it is noticeably more accurate than physics-based simulators, even if we apply very extensive system identification. Our proposed framework can also be applied to perform other tasks, for example, such as shaping the dough into complicated letter shapes. Highlighted in the middle by the red rectangle is the manipulation results of manipulating this deformable dough into letter shape like R, O, B, C, and K. And it's together will spell out the name of our project like Robot Cook. The right side of the figure displays the results from the baseline, which demonstrates significant larger deviations from the targets. Here we provide quantitative comparisons between our method and the baseline. Our method consumes the least amount of time and achieve significantly higher performance as measured by human studies. We ask the human, can you recognize this letter? And if you can recognize it, which one it is? And our results is much better than all the baselines. Notably, we compare our work with a baseline that does not learn a policy, but instead directly plan using the learned dynamics model, using sampling-based trajectory optimization techniques. This method requires much more time and achieve substantially poorer performance, indicating the importance of this self-supervised policy learning procedure using the learned dynamics model. We also compare our methods with a baseline that use a state-of-the-art physics-based simulation method, which is named the material point method, abbreviated as MPM. We observe that even with extensive system identifications, the identified MPM simulation is still noticeably worse than our dynamics model in terms of the prediction accuracy. And our model only learned from real data turns out to work the best. And so far, what we have talked about is a combined use of particle representation and graph neural network. It is the structure we use to capture the structure and compositionality of the underlying systems. It allows us to model the dynamics, for example, rigid objects and their interactions with fluids, as well as the dynamics of deformable objects like plasticines and dough. And we are also modeling the interactions between such objects with various of different tools. We have also shown, like using the learned dynamics model, we are able to accomplish very, very complicated long horizon manipulation tasks like dumpling making. It involves both the planning at the task level and the motion level, where we are making both discrete decisions, like what tool to use, and then the continuous decision, like condition on the tool, what specific action to take. But however, for all the tasks I have shown until now, what we use is a fixed resolution particle representations of the environments that represents the objects of interest. And next, I would like to argue that a fixed resolution representation of the environments may not be the most effective one. And essentially, what we want is a dynamic representation of the environments. Here, I'm giving you a very simple example. Let's assume we want to grab some objects that are far away from you. When the object is far away from you, you only have to know there's an object out there. As you're getting closer and closer to that object, you have to focus more and more on the details and local geometry of that object in order to grasp it. So even for this one single task, the most effective representation might need to be dynamic throughout the execution process. Not to tell what if we are handling objects of wide variety of materials, rigid object, deformable object, articulated object, closed, rope, etc. So I would like to argue that the most effective representation needs to be dynamic. And for this specific work, we are using object pile manipulation as a test bed to study how we can automatically learn dynamic representations of the environments. As I have shown in the very beginning, object pile manipulation is a common task we typically encounter in our daily life, like in the kitchen environment, or if we are, for example, sorting some like medicine pills. And again, we're representing the object piles using particles. But the question is, given the current observations of the object piles, how many particles do we assign to represent this pile? And for example, we can use more particles or fewer particles, depending on the resolutions we want this perception module to condition on. If we use too few particles, for example, if we just use 2 to 3 particles, it is ineffective at modeling the shape of this pile. If we use too many particles, it is inefficient. For example, if we use thousands of particles, imagining the message passing process within the graph neural network, it will take a lot of time to evaluate the effects of a specific input action. So how to choose the number of particles, choose the resolution of the environments becomes the question. And I would like to argue that a good representation needs to be minimum in its capacity, but sufficient for us to do the downstream task. And in order to find the optimal resolutions, we are essentially conditioned on our systems on both the current states and the targets. Given the current state and the target, for example, here the target is to gather all the object piles into the regions highlighted on the bottom right. And we want to use this kind of abstraction level or the resolution that is the most effective and maximizing the task rewards or minimizing the task cost. And we are using Bayesian optimizations to do the optimization. Specifically, given the current observations and the target we aim to achieve, and here is the cost of using different numbers of particles, different resolutions to describe the environment. As you can see, we observe this very nice trade-off. When we use too few particles, it is ineffective at modeling the systems. If we use too many particles under a given time budget, the optimization is inefficient in terms of finding a very good action. And similarly, if we change the target's region, for example, it's exactly the same initial observation, but when the target becomes more complicated, you realize the optimal resolution becomes higher. That means the same current states, but more complicated targets might imply the necessity of a higher resolution dynamics model. And on the other way around, for example, given the same states, given the same target regions, if the initial state is very spread out and compare with the initial state that is very close to the targets, we will realize that when the pile is close to the targets, we actually need a higher resolution dynamics model that to reveal the subtle difference between the pile shape and the targets in order to make progress on this task. And when the object pile is very spread out, there's a lot of actions that can make progress in the task. That means we don't need that fine-grained of a representation to model the environments. So same targets, different current states also implies different resolution. And then basically, given the current observation and the targets, we use Bayesian optimization to obtain the label, and we train a resolution regressor to predict the optimal resolution during test time. And conditioned on this resolution, we have a perception module that can generate a set of particles that representing the environments. We can then have a graph neural dynamics model that predicts the evolution of this particle sets conditioned on input action sequence. And one thing I hope to highlight here is that we don't have to retrain the dynamics model when we use different resolutions. As long as the node encoder and the edge encoder is conditioned on the resolution parameter itself, we would be able to allow this model to generalize to systems containing different numbers of particles, because that's essentially what graph neural networks do. So we don't need any retraining, just one unified dynamics model will be able to make such kind of future prediction. Then we can define a loss function that measures how close we are in terms of accomplishing these tasks, and using gradient descent to backpropagate the gradients of the loss function with respect to the action signals to optimize the action sequence. And here is the real-world setup we are using to do this object pile manipulations. And we are evaluating our systems on object piles of a wide range of granularities. The first task we are thinking about is to gather the objects into some target regions. And you can see from the videos, we are handling objects of very different granularities. Some are very, very small, like rice. Some have more bulky piles, for example, like the candy and carrots. And the same model, without any retraining, without any online adaptations, is able to make very effective progress on this gathering task. And again, our model is not perfect. So when we deploy the system, we will always have feedback from the environment to correct our model's prediction accuracy, to correct our model's prediction error and give the model an opportunity to adjust its subsequent action sequence. And we can also ask the model to push this object house to achieve some more complicated target shapes. And you'll very quickly realize what the target shapes are in this case. Here we are pushing this object house into achieving the target shapes of all the English letter shapes, all the way from letter A to letter Z. I would like to argue that nobody else have shown result like this, and it is actually non-trivial in a sense that it involves some non-trivial redistribution of the object pieces. Some how much pieces should go onto the top, some how much pieces should go onto the bottom. And after you do this kind of redistribution, you have to align these fine details to make sure it actually aligns with the target shapes we desire. And besides these English letters, we have also tried, for example, Chinese characters. This translates to hello world, as well as Japanese characters. This is konnichiwa, which is also translates to hello. So we can achieve these target shapes with very good accuracy. So to summary, in the talk I talked until now, we have discussed the combination of particle representation and graph neurodynamics model the dynamics of objects that are compositional and always high degrees of freedom. We have shown very effective use of such models for very complicated tasks like manipulating forms, manipulating object house, and even make a dumpling out of using our neurodynamics model. And it comes with two major benefits. The first one is generalization, where our system can naturally generalize to systems that are larger than during training. As I've shown earlier in the talk, where even if there's more fluid particles, our system is able to handle that. Our system can also achieve unseen target shapes. For example, the data we use to train our object power manipulation models and the dumpling making models are just random interactions of the robots with the environments. But because these structures in our systems, we can achieve this regularly distributed object piles like the letter shapes during testing. The other major benefits is sample efficiency, where just 20 minutes of real-world offline random interactions of the robots like interacting with the DOF will be able to learn a very good dynamics model that is even more accurate than state-of-the-art physics-based model. And I have also discussed how we can use Bayesian optimizations to dynamically select the optimal resolution to strike the optimal trade-off between efficiency and effectiveness. And start from my very early work on using particle dynamics, this thread of work also inspired two major threads of follow-up work. The first thread of follow-up work is using graph structure neurodynamics to model the dynamics of large-scale compositional systems. Here are some works I particularly like from DeepMind, Intel, and Stanford on the modeling of large-scale particle systems, intuitive physics, and mesh-based systems. Another thread of follow-up is to use particles as a representation for deformable object manipulation. Here I'm showing some particularly interesting work on the manipulation of amorphous materials, clothes, elastic materials, as well as a benchmark from CMU on deformable object manipulation. And finally, I would like to thank all my collaborators on this project I have shown. Without them, it will be impossible to do all the work I've shown here. So yeah, I'm just showing the summary slides, and I'm happy to take any questions.